All right, hello and welcome to Friday, everybody. And now we'll get started. Okay. All right, that's better. Okay, so let's just look at this tubular secretion thing again. I think we left off looking at this image. It shows where different things are happening in the kidney within the tubule. So remember, the last process of the kidney is secretion. So we're going to occur into any part of the tubule, actually, and additionally the distal convoluted tubule. So hydrogen ions, potassium ions. So remember, if we're going to control acid-base balance, we will be secreting hydrogen ions into the tubule. If we're trying to regulate sodium balance, if we're reabsorbing sodium, we're going to have to excrete potassium. Creatinine, part of our protein metabolism. Same with the ammonium ions, protein metabolism. Organic acids, lactic acid stuff, other acids that we make, pyruvic acid. Drug metabolites, urea, protein metabolism, uric acid. So to clear out that extra stuff, then we're going to be doing tubular secretion. Like it says, to dispose of substances not already in the filtrate or eliminate undesirable substances that were reabsorbed, get rid of excess potassium and control pH. All right, so we've already gone through how the loop of Henle works, but we need to discuss it in a bit more detail so that we really get a good understanding of what is the purpose of the loop of Henle. So in order to make sure that our solute load is always 300 milliosmoles, which is what our plasma is, it's our interstitial fluid, it's our intracellular fluid. So osmolarity, 300 milliosmoles. So osmolarity, again, is the number of solute particles that you have in, oh, it's right here. The concentration. So it's not really a concentration per se, but it's an actual amount of particles. Because when you're calculating osmolality, they're about the same thing. When you're calculating osmolality, you're looking at a gram of a substance. Well, you're looking at a mole, actually. A mole of substance, so that's going to be molecular weight. So a gram of the substances of the molecular weight. So it's not a concentration amount, but how many actual particles do you have? So it's going to take in Avogadro's number and all that stuff, and how much do you have in a milliliter or a kilogram of water? And so we need to make sure that everything stays at 300 milliosmoles, because that's how we determine where fluid is going to go in the body. And so by changing the osmolality of a particular substance or a particular fluid compartment, then we can get water to move from that fluid compartment to another one or into that fluid compartment. So it's all about making sure my solute load is where it's supposed to be. So that is my kidney's prime directive, essentially, especially even with filtration, because once you filter, you've got to reabsorb the right number of particles so that you're maintaining that osmolarity. So by regulating urine concentration and volume, the body fluids and plasma remain fairly uniform. That's what we're after. All right, so we know that we're going to drink a whole lot of water during the day, and we can't keep all the water that we absorb. We have to get rid of enough so that we go back to 300 milliosmoles. So what are we going to do with the extra water? We're not going to keep it in our bloodstream, because that's going to produce too high of a blood pressure, and then we'll have cardiovascular problems, and so we have to get rid of the extra water. So that's why we want to have a dilute urine. And so it's necessary to dilute the filtrate as it passes through the tubule. So how do we dilute the urine to filtrate? Well, you can do two things. When you're diluting something, typically when we dilute something, we add more water. But you can dilute something also by taking out the solute. And that's what our loop of Henle is going to do instead of putting water into the tubule, we're going to take solute out of the tubule. So that's this bullet point right here. Will reabsorb a higher proportion of solutes than water. And normally this would not occur. We couldn't reabsorb more solute than water because the filtrate has the same concentration of blood after we've been through the proximal convoluted tubule. We're still at 300 milliosmoles. So how do you take more in when you're at equilibrium, or how do you dilute the urine when you're in equilibrium? So that's the function of the loop of Henle. So there are some interesting characteristics that we've looked at already. We took a look in lab, and some, not this last one, but the one before. And so we need to revisit those tissue characteristics so that we can see how is it possible to go from 300 milliosmoles to 100 milliosmoles. So we need to take a look at a cross section through a kidney, and we need to take a look at the interstitial fluid concentration or the osmolarity of the cortex, and then we need to look at the osmolarity of the medulla. And if we see in all portions of the cortex, the osmolarity is 300 milliosmoles. It's all isotonic. Okay, but then as we start to dip down into the medulla interstitial osmolarity increases, and it becomes 4 times more than what we have in the cortex. And so why do we want to make it 4 times more than what we have in the cortex? Well, we're going to take a look at that. Okay, so remember, the medulla has an osmotic gradient, is what we call this, because up here there won't be as much osmosis, but down here there'll be a heck of a lot of osmosis coming out of the tubule. Okay, so remember, medullary osmotic gradient is this increasing osmolarity of the interstitial fluid of the medulla. Okay, so now how are we going to achieve that? So we're going to take a look at this picture, and then we'll go through in our notes all of the little steps that are happening. Okay, so if we look at up here in the glomerulus, we're going to filter until we're isotonic, and so then our filtrate is isotonic, and we're going to reabsorb so that our filtrate remains isotonic. But as soon as we get into the thin descending limb of the loop of Henle, which is made out of simple squamous epithelium, it's permeable only to water. So remember, the thin descending limb is permeable only to water. Okay, so freely permeable to water. So we're going to have lots of water channels in these simple squamous epithelial cells, and not at all permeable. So there's no channels for solute, so sodium and potassium along here, because that's really all we got left, right? Sodium potassium chloride, because we absorbed everything else right to this point. So we absorbed the glucose, we absorbed the amino acids, our vitamins, and all that great stuff like that. Okay, so notice also that water is leaving passively, because remember, we never ever have active transport of water. It's always a passive process. So how are we going to make this water want to come out when I'm losing water, losing water, losing water? Okay, so if I'm losing water here, what's it like inside of my tubule? Well, my tubule is also getting more concentrated. And so what do I have to do to the outside so that water will want to come out? Because remember, you've got to move from dilute to concentrated. And so what happens in outside of here, we have to make it more concentrated than what it is inside of the tubule so that the water will want to come out. Okay, so how do we do that? How do we make the outside of the tubule? And it's not just this side, you guys. I know the picture always looks like we're moving it out to the left, but we're not. We're moving it out of the left-hand side. So we're really not just moving it to the left side of the tubule. We're moving it to the entire surroundings of the loop of Henle. Okay, so get that in, get a picture that we dunked. So let's say we have a beaker of really salty water that's that has layers in it. So it's less salty up at the top and more salty down. Well, let's use Jello because that's a better consistency. So we have like super pale Jello up at the top, and then it's like ombre Jello. Oh, that's a great visual. Okay, so I got a beaker of ombre Jello. So it's really light up at the top and it's super dark at the bottom, and I stuck a tube of water into that. Okay, so get that picture in your mind. In fact, I may even draw something, make something like that for Monday so that you can have that forever. So we've stuck this tube in, and so what made it this Jello ombre color, okay, or situation? Well, it's what we did over here on the ascending limb, and especially in the thick ascending limb. All right, so the first thing that is going to go on and here's what we have to do. So we have to loop it. So we can't just stick a straw down through and have these conditions happen. We have to flip the tube. So we've got to loop it around and make it come up the other side right next to the descending limb so that the conditions on the other side are opposite to the first side. And so what we've made down here is this super, super concentrated filtrate down here. And as we turn the bend, what we're going to do is also absorb urea out of the urine, so that we want to put this urea back into the filtrate. And now what we're going to do is, for a little bit till we get to the thick ascending limb, we're going to have a little bit more concentrated in our tubule so that the sodium chloride is just going to want to passively leave. So we're going to go around the bend, and urea comes in and sodium chloride comes out. But then when I get to the thick ascending limb, I'm going to go make sure that that ombre still works. So I'm going to pump sodium chloride out, pump sodium chloride, pump sodium chloride. But I have to pump too, because I've turned the bend and stuff is leaving. So I don't have as much tendency for this to leave. So I have to pump it out now. And that's fine. I have those sodium potassium 2 chloride channels, and I'm just going to pump the stuff out into the tubule. Okay, so that's going to come out here. Okay, so now what is that doing to my surroundings? It's causing me to have this increasing osmolarity of my interstitial fluid. So it's going to go, and this 300, 400, 600, 900, 1200, this is going all the way across here. Okay. And so now if I'm pumping if this solute is leaving and I'm pumping it out, look at what happens when I get to the distal convoluted tubule and collecting duct. Okay, it is all 100 milliosmoles. Okay, so look at what happened here. I went in as 300 milliosmoles. I came out as 100 milliosmoles. So I'm 3 times more dilute on this side than I was over here on this side. And then we're going to keep everything the same. We're just going to keep it 100 milliosmoles as we go on out through the collecting duct and into the calyces, out through the papilla and the calyces and the pelvis and the ureter and the bladder, urethra. But if we're in a situation where we're dehydrated and we have two hormones, aldosterone and ADH, then this is going to change. And we're going to take a look in the next slide, on the next diagram, how that has changed in the presence of ADH. Now, okay, let's go ahead and look at our notes. And then we're going to come back to that vasa recta in a minute. Okay, so the descending limb of the loop of Henle, impermeable to solute, freely permeable to water. So filtrate becomes more concentrated as it reaches the bend in the loop. Simple squamous epithelium is the tissue type. Okay, then in our ascending limb of the loop of Henle, impermeable to water, actively transports sodium chloride into surrounding interstitial fluid. This dilutes the filtrate until it becomes very dilute, more dilute than plasma or interstitial fluid in the distal convoluted tubule, and it's distal convoluted, simple cuboidal cell. I don't know. Whoever had a question didn't. I mean, my speakers are still here and they're still working. So if someone has a question, then go ahead and text it. I mean, chat it to me or unmute yourself or something. I'll wait for a second.
Can you hear me?
Yes.
My question was just, what does urea do to decrease the osmolarity when it comes out of the collecting duct?
It's not going to really do that much. Its purpose in coming out is really to keep the medullary osmotic gradient more concentrated, and then also to go back into the tubule so we have more solute to leave. It's kind of complicated,
So is it the passive salt that starts bringing it down?
Well,
Like,
yeah, down at the bottom of the tubule, yes. Yeah,
okay.
exactly.
I was just wondering what made it start going from 1200 and really concentrated.
It's the passive sodium at the bottom of the tube, because that's where it's the most concentrated.
Gotcha.
At the loop of the tube. Yeah. Okay. Gotcha. And Josh, there's just renal physiology. I could teach you a whole semester just on renal physiology. So there's a lot more to it, but
yeah, that's what it seems like. It is really interesting though.
It is well, okay, so like I told you, remember when I went to my cardiologist and he's like, oh, I love physics and I love fluid flow and everything, so I thought I've got to be a cardiologist so that I can use my, you know, my love of the stuff and
right.
and I'm like, no, I hate that. But I love the urinary system. I just love the sewer. I guess maybe I should have been a plumber in a previous life. But seriously, I love the urinary system, even in its complexity. But its complexity is amazing. And then the whole embryology of it and stuff is great. But oh yeah, it's rough. And this summer I have a course on renal physiology. So yay.
Oh my gosh, you never stop, huh, Miss
I
G?
know. Yeah, this summer I got renal physiology and endocrinology. And then
oh, endocrinology.
yeah, but that's my other love. So I really like that. And then I've got 3 more classes after that. And then I'm all done. Then I'm never taking another class again. So yay, yay.
Yay.
Yay. Okay, so sorry for that little break there, everybody else, while Josh and I chat. Okay, so then collecting ducts are permeable to, oh, so Josh, here's the answer to your question right there. Permeable to urea to maintain high solute concentration in the medullary interstitial fluid. And because it's osmolarity, it doesn't matter what is contributing to the solute. So it could be sodium, it could be chloride, it could be potassium, it could be urea, it could be anything. We just need it to stay, in this case, where the urea, let's go back to that picture. Okay, so where the urea comes in, we want to make sure that we have enough to passively leave right here as far as solute's concerned. And so, so by putting the urea in, whoops, where are we? By putting the urea in, that allows the sodium chloride to come out as far as to maintain the concentration inside of here. So we're really substituting, we put the urea in here to make it more concentrated, but then by keeping the solute load with urea instead of sodium chloride, then it allows the sodium chloride to come out, is the idea. So anyway, so that's what's happening there. Okay, so now let's go to the vasa recta. So that is this capillary here. And so what is the purpose of the vasa recta? First of all, the purpose is to make sure that the cells in the interstitium, or I mean the cells in the medulla, get oxygen and nutrients, and waste products are carried away. So we're just doing exchange like we typically do exchange. But because we've so messed up the interstitial fluid out here, we want to make sure that we maintain this 300 to 1200 milliosmol concentration gradient. And so we can't just run a blood vessel through here, because what's going to happen? All of the water is going to come out of the blood vessel and all the sodium is going to go in, because it's so concentrated outside. The water inside of the capillary would come out, and the sodium chloride in here would go in. And so that's what happens on the descending part of the vasa recta, on the afferent or on the arterial side of the vasa recta. So yeah, that's going to happen. And so notice what happens to the concentration of the blood inside of the vasa recta. It gets concentrated just like the filtrate gets concentrated in the loop of Henle. But what happens is that we come up the other side, because we loop it instead of just running it through down into, the bottom of the medulla to get back to the veins, to the renal veins. What we do is we loop it back up again into the cortex. So we're going to go, we came out of the cortex and we're going to loop back up into the cortex. So now what does that do? Well, it makes the solute concentration inside the vasa recta just slightly more than what it is outside at this point. And so the sodium chloride comes out. And then any water that's in here, because I've so concentrated the blood at this point, the water comes back in. And it's going to do that passively. Look at, these are just passive processes. It's just going by osmosis and solute concentration, irregular concentration gradient, diffusion. And it comes back up the other side. And look at what we did. We went in at 300, we came back out at 300. And so that's a beautiful thing. The ingenuity of this system is mind-boggling, and its perfection is so beautiful. And I guess maybe that's another reason why I love the urinary system so much, is that it just has it going on more than anywhere else in your body. We have serious osmotic stuff happening, and how do you figure it out so that you fine tune it to get it to the point that you need it to be is out of this world, friends. Absolutely out of this world for you to think, oh, well, that just kind of happened mutation by mutation over time. I mean, yeah, it did, but which mutation did you want to happen? That's the key. So anyway, just the whole kidney, just the evolution of the kidney, you guys, is just phenomenal. Okay, so now before we leave this, I need to show you something really cool. So when you're doing PhysioX9, there is a question about, in fact, let me go to that question really quick, because it's my favorite question in all the PhysioXs. And I am going to talk more about this on Tuesday. What are we doing on Tuesday? I don't even know. Are we the reproductive system already on Tuesday? Male and female reproductive. No. What are we doing on the 13th? Have I just so messed this all up that I don't even know what we're doing? Oh, wait a minute. Yeah, we must be doing reproductive. Oh, because I didn't draw an arrow. So we got to do reproductive, and then we do embryology, and then we do the lab practical. Yeah, because you know what, guys? We're almost done. We're done on the 8th. That's just craziness. Oh my gosh. Okay. So anyway, all right. So it's, if you have your lab manual with you, and that's fine if you don't, make sure you have it on Tuesday, because we'll go over it again. So activity 4 in PhysioX9, solute gradients and their impact on urine concentration. And so we will super go over that, because I love, love, love it. But on PEX 140, the activity question says, from what you learned in this activity, speculate on ways that desert rats are able to concentrate their urine significantly more than humans. Okay, so here's the deal. Kangaroo rats, my tortoise, birds, and geronix. I'll put a picture in of a geronix so that you know what it looks like, because we saw one at the zoo the Phoenix Zoo. When were we there? Anyway, all of those animals that I just listed, and lizards too, so most reptiles, I guess. I'm just particularly aware of what happens in a tortoise. They never produce liquid urine. Okay, so they never excrete. I shouldn't say they don't produce it, but they don't secrete, or they don't excrete, sorry, wrong word. They don't excrete a liquid urine. All of their nitrogenous waste comes out in either a paste, that's as wet as it's going to get, like in bird droppings, you know, the white stuff is the urea and uric acid, and it's kind of pasty. And then my tortoise, I showed you what my tortoise urine looks like. It's powder. What hers comes out totally in a powder. And desert rats, so kangaroo rats, geronix, also produce that same kind of thing. So let me show you how that works. So we're going to go to, let me draw in here. Let's do it in green. All right. So here's what happens in desert. Well, does anybody want to propose a mechanism for, based on what you can see right here with the loop of Henle, that would allow desert rats to super concentrate their urine? Anybody got a thought? Josh, Dixon, any ideas? Okay, nobody's got an idea. So I'll just tell you.
Would it be not adding as much water in, or not like removing as much water, because then it wouldn't be able to be liquid?
So how would I do that? Because you're on the right track.
By not releasing as much solute and
No.
therefore not diluting it as much, maybe?
Okay, no, because what I want is the water to come out, right?
Mm-hmm.
I want a powdery urine. So,
oh, so we need more solute to be released to make more liquid come out?
Water to come out, exactly. So how am I going to do that? Because you're so close. No, we're not going to change the permeability. It's all just the same.
Would you need like the gated, like the channels for?
Nope, channels are still the same. But good guesses, you guys. Good thinking, because you're looking at, hey, what is necessary?
Extend the thin portion.
Oh, yay! Who was that? Ray, was that you?
Yes.
Yay! That is exactly right. Oh my gosh, I'm going to cry right now because I was already having a stressful morning with everything I have to do today. And I'm like, oh, you got it. It makes me, I'm such a nerd. I'm such a nerd, but yes, that I cry and somebody got that. Okay, so yeah, look at what we're going to do. So Ray is exactly right. We're going to extend the loop. So what are we going to do down here? We're going to allow so much more water to come out so that we super concentrate down here. And guess what, you guys? This is the medullary osmotic gradient by the time. And so now we're just going to have so little water left down here that when we get back up to the top, there's like no water left at all. And so this is, you know, we think, holy cow, this is, you know, 4 times more concentrated than what it went in. Okay, so if you're a kangaroo rat, guess what? It's 20 times more concentrated down here at the bottom. A geronix is a mammal. It is the only relative to the giraffe. And you did spell geronix right. Very good. It kind of has a long neck, has big ears, and yeah, they live in desert kinds of environments. And so, and they're really cute, and they stand up on, so because their necks are not as long, they'll stand up on tree trunks. Like they won't get into the tree, but they have super long legs, like giraffes do, but they just don't have the long neck. They're not as tall at all. But yeah, so they're the only living relative to the giraffe. And so they stand on the trees and they up the trunks and they eat the leaves off the trees. And so anyway, I'll put a picture in there. But yeah, they're the only mammal other than, you know, big giant kind of mammal, like the kangaroo rats that have pasty urine. So anyway, but yes, and so that's, in fact, the kangaroo rat, I was reading and this was actually a journal article that I was reading because I was doing some research on it. And the kangaroo rat has the longest loop of Henle of any animal. It was really crazy. So they just super descend down into the medulla. Okay, so yay, that's so beautiful. What a happy day. See, you guys just make my day. I come in going, why are we even going to school today? Because it's Good Friday and I can't even celebrate Easter or nothing, and I feel better now. Okay, so what does the vasorecta do then? Prevents too much reabsorption of salt and water that would decrease the nephron's ability to dilute the urine. And it preserves the medullary osmotic gradient. Okay, so now we're going to take a look at what does ADH do. So here is our normal loop of Henle and collecting duct, distal convoluted tubule and collecting duct. So here is everything, you know, the way it's supposed to be, nice dilute urine. But then in the presence of, let's do it. Okay, so in the presence of aldosterone, right here, not aldosterone, in the presence of ADH, right here. Okay, so we're going to increase the number of aquaporins in the tubule cells here. And so water will just come in on the luminal side. So that's where the aquaporins are, is on the, you know, the side facing the tubule. So we put the aquaporins in and then water just gets reabsorbed. And obviously water gets reabsorbed because look at it, it's just coming out everywhere. Plus, what's the medullary osmotic gradient that we have right here? Sure, water is going to want to come out. We have to work real hard to keep the water in to make sure that it's not. And so we have this great mechanism of collecting back this stupid water, is what we called it a few semesters ago. It was like, well, that's stupid water. We shouldn't be getting rid of water in our filtrate if we're dehydrated. So yeah, so think of when we're dehydrated, what stops? Sympathetic stimulation and the presence of now low blood pressure in the kidney and the release of renin and now the release of ADH. So I stop getting rid of water in my urine. I stop sweating at, you know, some point. I get to the point where I stop sweating. Then you know that you're really bad off, is that if you're hot, you know, and you've sweated and then all of a sudden your body goes, I can't lose water through my sweat, and then you stop sweating and now you know death is imminent. Or imminent, not eminent, imminent. Saliva, you know, so those are places where we can draw our extra water from that we don't want to be wasting. Okay, so so notice now what is the concentration of my urine is 1200 milliosmoles. It's isotonic here to my interstitial fluid, and so that's when it looks like really yellow and bad, you know. And then it just depends on how much ADH was released, is how much water gets reabsorbed, you know. So you're not gonna release the same amount of ADH, you know, because if you just reabsorb back a little bit of water, then your plasma osmolarity is restored and you don't need to release ADH anymore. You know that when your urine's super yellow that you haven't been drinking for a while. Okay. Well, okay, Josh, there's going to be a whole lot of other problems that are going to happen as well. I'm not going to become hypernatremic as much with sweat, because remember, sweat's not isotonic. Sweat's really hypotonic. Something like diarrhea or vomiting would make me, hypernatremic. I was going hyponatremic. So yeah, I am going to be hypernatremic. If I'm sweating a lot, you know, losing a lot of water, but that's going to be, I'm going to have issues before that But yeah, if I have hypernatremia, then sure, my heart's gonna go into arrhythmia and I'm gonna die. Yeah, so, but remember, sweat does have some salt in it, so I'm gonna lose some of it, but yeah, so, okay. And then when we go to lab, when we go over PhysioX 9, we're going to talk about some diuretics. Oh, we're going to do diuretics here in just a minute, but we'll talk more about the action of diuretics. So Josh, you'll be happy with that after your whole pharmacology stuff. Okay, so let me go back. Okay. All right, so in the presence of ADH, aquaporins or water channels of the collecting duct increase in number and the filtrate loses water by osmosis as the duct passes through the medulla of the kidney. Okay, so we've got that. So there's that. Okay, so diuretics. Like I said, we'll talk more about diuretics in lab because we've got 3 kinds of diuretics. We've got thick ascending diuretics, we've got distal convoluted tubule diuretics, we've got collecting duct diuretics, and so we'll just quickly look at all 3 of those. And so anyway, so what is a diuretic? It's something that makes you go to the bathroom. So it's a chemical that enhances urinary output. Glucose can be a diuretic because, yes, potassium sparing and potassium wasting ones. Yes, we'll go through all of those. So I just lost my thought. Oh, okay. One of the symptoms of people with diabetes mellitus is polyuria. They go to the bathroom a lot. And so now you should be able to tell me, why do diabetics urinate a lot? So I'm just going to pause for a minute, see if someone can now at this point tell me, why do people that have diabetes mellitus produce a lot of urine?
Is there too much glucose and not enough carriers?
Yes. So why would having too much glucose in my filtrate and not enough carriers be a diuretic? And not trying to lower glucose, because they're not trying to do it, it just goes out in their urine. But why would you produce a lot of urine if you had a lot of glucose in your blood or in your filtrate? Well, okay. It's not to dilute it, but it's the result. Okay, so it's a bad thing, and that's not our mechanism to do anything with the glucose. So here's the deal, is that if I have a high osmolarity of the filtrate, where will the water stay? Will it go out of the tubule, or will it stay in with that higher osmolarity of the filtrate? Am I supposed to have glucose in there? No. And so now if I keep the solute in my tubule, the water on the thin
right?
What?
It's going to want to stay in,
It's
right?
going to want to stay in. Exactly. Okay, so let's go back to that thin descending limb. Okay, so here we have the water's going out, but if I keep it higher inside of here than what is outside of here, what's the water going to want to do? It's going to want to stay. And so by having a lot of glucose, because remember, it's osmolarity, it doesn't matter what's inside of here.
It matters what's outside of there.
It matters what's outside. So if you have, well, yeah, but I mean, what I'm saying is it doesn't matter what constituent it is. It could be glucose, it could be sodium, it could be potassium, it could be chloride, it could be any solute. It doesn't matter what solute it is. What matters is how much I have of it. So if I couldn't get rid of all of the glucose right by this point right here, is there anything on this side that's going to pump out the glucose?
No, nothing.
No, nothing. So the glucose is going to stay. So now what's going to happen is that this medullary osmotic gradient is not going to be as high as it needs to be. And so the water is going to stay, just like when we have our other loop diuretics, Josh, when we have, the ones that are over our thick ascending limb. What do? We keep the sodium in here, right? We don't get rid of the sodium. And so then the water stays, and then we produce a lot more urine. Okay, so that's why glucose is a diuretic. Okay, alcohol is a diuretic because we inhibit ADH. So even if I was trying to secrete ADH over here, even if I needed to secrete ADH over here, the alcohol would stop me from doing that. And next week we'll talk some more about alcohol and being a diuretic, because it's kind of a interesting feedback kind of thing that goes on. And then it's a bad feedback mechanism, actually. And then caffeine, because if we're inhibiting sodium reabsorption, sodium stays within the tubule, and so the water stays inside the tubule, and then you urinate a whole lot out. Okay, so, but again, we'll talk more about diuretics next week.
Why is it that when you drink like soda or something like that, you almost feel dehydrated? Because I was thinking
probably because of the solute that's in it, that you're reabsorbing more stuff than if you just drank pure water. You know what I'm saying? It doesn't have the diluting effect of your bloodstream that, when you reabsorb it, that water does.
Oh, okay.
Does that make sense?
Yeah, that does.
Okay.
I was thinking it would be the opposite because you feel so thirsty, but that makes sense what you were trying to say.
Okay. All right. So here is the last thing that we're going to look at for today is composition of urine. So what should be in our urine, and then we're going to look at what should not be in our urine. Okay. So the first thing is urochrome. So all of our, what is the way that we excrete things? Sweat, urine, feces. Okay. So we need to get rid of when we break up our red blood cells, remember we need to break down hemoglobin. So we're going to save the iron in hemoglobin, and we're going to get rid of everything else. And so part of that pigment, remember when your bruise gets better, that your bruise looks yellow, okay, because hemoglobin is being broken down. And why you look yellow when you're jaundiced is because that hemoglobin is breaking down and the liver's not taking it out. And what's left in your bloodstream from what your liver didn't extract now is going to go out in your urine, and we call it urochrome. Okay, so that's why your urine is yellow. pH of 6. Okay, so it's slightly acidic. And why is it slightly acidic is because typically we produce lots of acids as we go through our ATP production in our bodies. And so remember, our kidneys are for acid-base imbalance or homeostasis, sorry. And so when we absorb sodium, remember there are those hydrogen antiports. So as we absorb sodium, we send out hydrogen ions. And so that's what makes our urine acidic. But that's a good thing because we don't want any urinary tract infections. We don't want yeast infections. And so by having an acidic urine, it helps keep things from growing in our little tubes that we don't want things to grow in. We should have nitrogenous waste, obviously, urea and uric acid, creatinine too. I should put that on there, but whatever. We can have some sodium in there and potassium in there. And then whatever materials from tubular secretion. Okay, because if we're trying to maintain, our electrolyte balance. Okay, so it just depends on what we're eating, you guys, obviously. All right, then what shouldn't we ever see in our urine? We should never see glucose in our urine. If we do, then we ate a whole bunch of sugary foods. So let's say, I love Easter candy more than even Halloween candy. I love all the Easter candy. And so if I ate all that Easter candy and then I'm going to be diabetic for a moment, right? And as I absorb all of that. And then if I just ate so much, then yeah, some of it's going to go out in my urine. So guess what, friends? There are times when, yes, you do have glucose in your urine because you ate so much that your body couldn't handle it. Like Aaron just said, I don't have enough workers. I don't have enough transporters. But when do we test to see if you're diabetic? We don't test you. We don't check your urine or your blood, right, 2 hours or 3 hours after you ate a whole bag of Easter candy. No, we wait until you have fasted. Okay, so overnight. And then we check you, and then we see, oh, so any glucose that you might have had, has your body been able to take that up? Yes, that's when we check you. If there's anything else left in your blood, in your urine, then yeah, you have diabetes. Okay, so don't worry, friends, that there will be times that each one of us will have some glucose in our urine, but that's because we took in too many sugary foods. But then our body will get rid of that extra, and the insulin secretion will cause it to drop in our bloodstream, and then we'll be fine. Protein, never ever protein. Well, I shouldn't say that. Sometimes, yeah, excessive physical exertion, because freaking what did you just do? You just worked out so hard that you broke up all the actin and myosin in your myofibrils, and yeah, you can get some proteins in your urine. Pregnancy, because of your blood pressure that's in there, because how much more fluid, what is it? I can't remember. How much more fluid do you not take in, or produce when you're pregnant? It's like craziness. And that's why we always have to worry about preeclampsia and eclampsia going on. We want to make sure that your blood pressure is where it's supposed to be when you're pregnant, because then you get, bad problems with your placenta. I can't remember the volume, but yeah, during pregnancy, we can have so much pressure that we push some proteins out. And then this has always been my curiosity here, is a high protein diet, ketogenic or Atkins. It was when Atkins back in the 90s or whenever that was. And I wondered about that. And I thought, well, how much protein, if we're just eating protein, how much is actually going to end up in our urine? And are we going to be in metabolic acidosis and all the time? Because that's where you want to be if you're on keto, because right, what are you trying to get into? Ketoacidosis. So anyway, that's just my ramblings. In the feces, because it would get reabsorbed. Well, okay, so think about if your muscles are breaking down, that it's going to go into your bloodstream. And remember, feces don't eliminate anything that's in your bloodstream. They just eliminate stuff that's in the excessive stuff in your food, so that it would just be in your bloodstream, that the proteins being broken down by physical exertion would only end up in your bloodstream and not out in your gut tube. So that's why it wouldn't be there. Okay, ketone bodies. So we don't want ketone bodies in our urine again. This acidity, because that metabolic acidosis, friends. Okay, so starvation, untreated diabetes mellitus, or not so ketogenic diet, I would imagine. So I don't know, but that's going to screw with your pH. That's why we don't want them there. Hemoglobin, obviously, we don't want hemoglobin in there. You got serious bad stuff happening. I don't know. Biopigments, we don't want that in there either, because then it means what? Our liver is not functioning, right? Because where's the bile supposed to go? Now that product is supposed to end up in our gut tube, in our feces. But yeah, if it's not getting in there, then it's staying in our bloodstream, and then we get cirrhosis. Then we get jaundice. Okay, so we don't want that in our urine, or we don't want red blood cells in our urine. Typically, that's diagnostic of kidney stones, because the kidney stones are going to scrape as they go along the ureter, and so make it bleed. And then we don't want any pus. Ooh, my internet connection is unstable. Okay, hopefully it's okay now. And then my urinary tract infection would be because I have pus in there. So I don't ever want pus in there either. Okay, so that's the end of our urinary system. I know we're like a day ahead, but we're going to have to shift things when we get to the end to figure out when we're going to take the last couple tests, because we got everything scrunched to the end. So we're actually in a good spot. We're kind of ahead, and so yay. So have a great weekend, you guys, and for those of you that are fasting with me, you know, let's pray today. For those of you that are not, let's just have great thoughts and hope that we can come together as citizens of the world and do what we need to do to help with this. You know, I felt this morning, I was like, oh my gosh, it's been so long. And I thought, no, it hasn't even been a month yet, you guys. When you really think about it, we haven't even been doing this for a month. So we're fine. We can handle this, but we just don't want people to die. And we want support for our healthcare workers on the front lines. Bless their hearts. Just keep all of these people in your thoughts and your prayers, and let's hope that we can get over this hurdle in our society. And I'm interested to see what comes out on the other side. I was reading a thing. I guess I don't have to record this, but too late, I didn't. I'm still recording. I read an article. I don't like to read COVID-19 stuff, because if it's not scholarly, I just am like, nope, I don't need to look at, so many range of things of information. But this was interesting. I think it was Fossey that said that we may never shake hands again after this. And Trump has said oftentimes that he's a germaphobe as far as handshaking. He does not like to shake hands, and he thinks it's a barbaric ritual anyway, because it kind of is when you think about where did it come from. It's you extend your hand to your enemy to show you do not carry a weapon in it. That's why we shake hands. That's where the handshaking came from. So I like, other cultures like namaste. I love that one, just put your hands together and bow your head. I love that. I love that greeting. So I don't know. It'll be interesting to see what comes out in the end after all this. I guess I can just stop this now. Okay. So that's that. Okay. So that's everything for the rest of this week. So have a great weekend. Let's see. I guess we got nothing heavy duty we got going on yet. Oh, I know. So work on your ABG problems this weekend while you don't have a lot of other stuff to, focus on, and homework and that kind of thing. So PhysioX10 is on acid-base balance. So that goes along with what we did in lab and the extra little thing that I did for the ABGs. So yeah, take a look at that and whatever, and then we'll just, so go get your, oh no, we're still fluid and electrolyte balance. So yeah, you still have your notes, so you don't have to print out any other notes. Okay, so if nobody has anything else to ask, then we'll just stop for today. And
how about quiz 11? When is that going to be up? Was that supposed to be due this week, or is that not?
Let's see.
I mean, I'm good with not taking it.
No, I thought I did that. What is it? Let me see. Let me go in here and find out. Okay. So it's due Tuesday. Is it not? Oh, it's not published. Oh.
Yeah, hey, I didn't see it.
I'm so glad. Holy crap, I have it all ready to go and it just is not published. Yeah, it's all set. What the freak? Publish. Bing. Now it's there. Holy crap.
And that's all over the fluid and electrolyte.
That's just on the
acid-based
fluid
challenge,
and the
right?
the water stuff, not any ABG stuff. Just
Right.
where it starts. Holy crap! How did I not? I must have just hit save and not publish. So where fluids are absorbed. So in here to the end.
Okay.
Yeah. Thank you. Thank you
You're
so
welcome.
much, Nicole. Yeah, I'm like, I know I did that. And I did that day before yesterday even. I did that on the 9th. Or I did that on the 8th and made it for the 9th. Because I didn't go to work. I didn't come to school at all yesterday. So, okay. Let me make sure everybody else's is published before I leave this. Nope, nobody's is. Oh, yeah. Just please, guys, keep me on track. Don't feel bad about, but what about this? Don't feel like you're that person because you won't be. Okay. They're all out there and ready to go. Let me see what my other little chat is. Thanks. Love you too. Thanks. I hope you guys have a fantastic weekend as well. And we'll see you Monday at 9. Bye.